Okay. Okay. So, I think we've been working on try and find a way to create a course for senior students to learn about digital and computer logic. However, first we're going to explain what exactly logic is. Sorry. We're going. Okay, so on the side of the tools there should be an icon with a star on it. If you click that and then just put it over wherever you're presenting from or listening in from, sorry. Okay. So we're presenting from Sydney, Australia, and looks like me listening in from the east coast of the US. Okay, so what is logic? Logic is used in everyday lives, even without us thinking about it. It's used particularly in the English language for reasoning and just for generally communicating. Some examples of logic in the English language are, for example, when I go to school on weekdays and not holidays, apart from today. During lunch, I eat my lunch or go to the library. Schrodinger's cat is an interesting one. Schrodinger it's about Schrodinger getting pulled over, and the idea is that you only know if logic is true or false if you're told about it. Otherwise, it can be in between. Other forms of logic. There's a couple of types of logic. For example, ternary logic, which is true, false, or halfway in between. Fuzzy logic, which is true or false determined by a percentage. Or Boolean logic, which can only be true or false. We're going to be focusing mainly on Boolean logic. Okay, so logic in electronics. Logic in electronics is mainly used for analog circuits to determine an outcome by having one or two inputs and providing an output of the result. For example, an inverter which would take a positive voltage and then output negative voltage, and the other way around. If nothing's going in, something's coming out, basically. Logic can be measured as a voltage. This shows what can be used as a water sensor with an input where it measures if the plant has water or if it doesn't. If the plant has water, then it sends a false signal as a low voltage on a wire, or then back to a controller. And if that controller believes that the plant needs water, it will send a true state to an output, which is being, in this case, a water tap that is controlled by a solenoid, which will turn it on and off according to what state it is in the logic on the wire. This shows a graph of voltage on a graph. The peak, sorry about the line being off, the peak is at 5 volts and shows the signal output is high, which means it's true, and the bottom of the valley shows the signal output is low, so the state is false. Logic gates. So AND gates. An AND gate requires both the first two inputs, here and here, to be powered to provide an output at this point at the end. And if either one of those two inputs doesn't have anything applied to it, or it is negative, then nothing will be coming out of it. sorry, these are slightly out of order. Right, OR gates. OR gates only, however, require one of the inputs to be positive or to be the true state for the output to become true. This allows you to have two streams and only require one of them to be true to have a total output to be true. Okay, so our solution to the problem of teaching high school students about logic gates are reprogrammable logic gates. We have created a device that would solve this problem, which, when connected together, will provide a different input or output, and they can be programmed to do different functions and provide different results. Okay, so reprogrammable logic gates have 4 ports. 2 of them can be used as either an input or an output based on what type of logic you want to provide. And the other 2 are just outputs. For example, if you would use an inverter which only takes 1 input, then you would use port 1, which is at the top at the red arrow, and the other 3 would be as an output. Okay, so how we made it. We firstly designed a schematic for the boards shown here. We then designed board layouts. Then we sent it to PCB, a printed circuit board manufacturer in Oregon, and we made, oh, sorry, wrong button. And we made these, well, we got these boards made. They were relatively cheap, $5 square inch for 3 of them, and we got 9 made altogether. And then we ended up soldering them, and they ended up being something like this, with parts being soldered onto the board. And to give you a perspective of how small they are, that's a ruler showing the different part sizes, and the part is the third smallest at the top, which is about 1 millimeter wide. Then after that, we soldered headers onto it, and we tried to program them. Okay, so our code example for an inverter is it basically runs on an AVR microcontroller, and here it sets out what pins are being used, and here it's detecting if there's an input, and if there is, turn the pins high, or if not, turn it low. We used an AVR AT-Tiny 24A, which is a low power microcontroller from Atmel. The advantages of having reprogrammable logic gates means that you can individually reprogram one or the other, so that even if you have a circuit that you've wired up wrong, instead of having to completely go back through it and completely rewire it, you just have to plug it into a computer and load a program on it. It also allows you to have a educational resource that doesn't require lots of different types of parts. So should they run out of one particular type of part, you can just reprogram the board so that it becomes another part. This is an application of logic gates that we've come up with. It shows a light sensor which has a high and low output. The high output being it was dark, and the low output being the lights on. It also has a infrared sensor which has a high of when there's an intruder and low when there's no intruder. They use an AND gate so that if both there's an intruder and the light is off, then it will set off the alarm. However, if the light is off and there's nobody there, or if the light is on and somebody's there, then it won't go off on its own. Alright, we came up with a problem that could be solved using logic. It's a cat door that's supposed to be able to let the cat in and out during the day, but only let the cats in during the night. The problem, so that the idea is that the cat can't get out at night. This shows a flowchart, and it has the cat being present, and it needs the cat to be present and for it to be daytime to let it in or out. But however, if the cat is outside and it's nighttime, then it will also open the door. But it will not open the door if the cat is inside and it's nighttime. This shows what is known as a truth table. It shows all the variables, and it shows whether they're true. If they're true and false, then what the output would be. So, for example, the first one is if the cat's present and it's daytime and the cat is inside, then the door will open. However, because it's for the second line, it shows the cat is present in daytime, but it's outside, and it's still true because it is daytime. Demonstration.
Okay, so what we have done is we made an example with an Arduino trying to create, well, basically recreate one of these in a simple form that is easy to demonstrate. So instead of having hundreds of, well, tens of these set up, then we just have, it's the exact same code, just running on an Arduino. So,
image is frozen. Yeah, there we go.
Okay. So, as you can see, the light's on. So, there is no input because, well, wire's not connected. But as we connect an input, the light goes off. And then when we disconnect it, the light comes back on. So we've tried to make this as simple to use as possible, and just to give you an idea on how these parts would connect together, just have a simple example. So we have one of these and just have a little header that just plugs into it. Then you can get another one of these boards and just connect it like that, and you can use it as like a wire or something else. Then you can also, we've also designed a board that will allow you to power it. So it would also have a header that you can just plug into the side of it, and then it will provide the logic inputs to actually run it. Now, these boards have to be programmed by a computer to change what it does. So we've designed a tiny AVR programmer board that will just plug right on top of the boards, and then it will be able to be connected to a computer and run a program that will be able to reprogram the boards. Might just go back to the other forms of logic. There's many other forms that can be used. For example, having in a computer software, so that if something happens, for example, a button press, then it will be able to respond in code by having something to log in or to give a notification or even to send a message somewhere around the world. But mostly, logic would most likely be used in computers. For example, the computer mobile device that you're using right now has thousands of logic gates inside it just to run it. In the CPU, there are thousands and millions because they're so tiny that they can fit it in an amount of space that can actually be used in a physical application that will be able to do pretty cool things like video, or in devices such as an FPGA, which is a field programmable gate array. It will be able to do a whole lot of things at once and multitask, so it can run one program and do another at the same time, and it will have enough space to actually run it. And things like even street lights outside, it can actually tell, like, if there's a car there waiting, and it will actually use logic, like if cars there and there are no cars in the opposite direction, then it will turn green so you can go.
In conclusion, we believe that logic can be used in many different ways for many different purposes. This uses, we've tried to come up with a way for students of schools in the modern world to be able to use devices that would use logic, and to learn about exactly how and why they use logic. We believe that there are other ways to possibly do this, but we've tried to come up with the best possible way that we can think of to demonstrate the uses of logic and different possibilities, that it could be used in.
Okay. Thank you for listening and watching to our presentation. We hope you had enjoyed it and think it's interesting.
Yeah, and hope to see you in the future.
Thanks. Does anyone have any questions? Okay, so it took us about 2 hours to do the schematic after researching, and yeah, basically worked the first time we had it made. In total, there were 3 people working on this project. One of us couldn't be here today, unfortunately, and we're possibly going to be using these to, we're possibly going to be using it in classes here at the school. Are there any more questions, or? At our school, we have many different classes for these. We have the software design and development classes in year 11 and 12, and currently Robin and I are doing a course currently called iSTEM.
So it's based on science, technology, engineering, and mathematics. It incorporates both the mechanical side of engineering and the electrical and programming side of engineering. It allows students to gauge quite the spectrum of different sort of applications engineering has in the real world.
Yeah, we're in a Catholic high school in Australia, so it's just a normal high school basically. Post-secondary, I'm thinking about going to the University of Sydney doing mechatronics and possibly becoming an electronics engineer and a software engineer.
I'm hoping to do a bit more on the mechanical side. I'm not incredibly good with programming, however, I feel I'm quite confident with mechanical.
Yeah, in our free time we do a lot of similar projects. For example, we've built quadcopters, and I did another project for a competition in 2013 with someone else, which is sort of similar. And I like doing electronic engineering.
Yeah, I've been working on building my quad up. I've also been designed a base camera gimbal for my quad. So yeah.
Spent a lot of time on it, and we've taken time out of our holidays and things to work on it. Thanks for watching and listening to our presentation. We hope you have enjoyed it. So thanks.
We look forward to seeing you in the future.
Thanks. Bye.